Hello, I welcome you all to this another interesting screencast. The problem reads blocks A, B, and C have weights of 50 newtons, 25 newtons, and 15 newtons respectively. Determine the smallest horizontal force P that will cause impending motion. The coefficient of static friction between A and B is mu s equal to 0.3, between B and C mu prime s equal to 0.1, between block C and the ground mu double prime s equal to 0.35. This problem is coming from the Engineering Mechanics and Statics textbook, 13th edition by R.C. Benam. Right, so we are going to be dealing with what we are calling a dry friction. Okay, which is the force that resists the movement of two contacting surfaces that slide or move relative to each other. This is a force that resists the movement of two contacting surfaces that slide or move relative to each other. So we are going to be focusing on three types of problems, three types of dry friction problems. And these are: one, where we have no apparent impending motion. Okay, this is the first one at the contacting surfaces or points. This is in a case where the number of unknowns are less than or equal to the number of the equations of equilibrium. So once we have this condition, we are also going to always check for slip at the contacting surface, and if this condition is met, therefore we are sure that there is no slip at the contacting surfaces. The second type of problem is where we have impending motion. We have impending motion at some points. These are points of contacts, points or surfaces. So these are contacting points or contacting surfaces. This is where we have impending motion at some. In this particular case, the number of unknowns is greater than the number of equations of equilibrium. In this particular case, we invoke or use additional equations from friction, which is F equal to mu n. Okay, because we can only solve the unknowns, the number of unknowns, or we can only solve the unknowns if the number of unknowns are equal to the number of equations, right? So that we are able to solve the unknowns, okay, simultaneously. In the third case, this is where we have impending motion. We have impending motion at O. Okay. So in the second case here, we are also going to check, because here it is the second case, it is some. So it means there are going to be some points where we are going to experience no motion. So we need to check using this particular equation. Okay. All right. So for the third case, impending motion at all points or surfaces. Okay. This condition, this also applies. The number of unknowns is greater than the number of equations of equilibrium. Of course, we employ additional equation mu n. Of course, here we don't need to check for any slip, because all the contacting points are going to experience impending motion. Whereas in the second case, some points, therefore, we are going to be forced to also check. We are also going to be forced here to check for F less than mu S for some points, for the other points, for the other non-impending, the points that are not going to be experiencing impending motions. Okay. All right. So I think in a nutshell, this is what we are going to be dealing with. So let's go to this particular problem. So we have three blocks here. They've got different weights, different coefficients of friction. And I want to find the minimum force that we can apply so that there is impending motion. So where do you expect impending motion? So this is type problem what? This is type problem. This is type 2 problem. Okay. This is type 2 problem. Okay. Type 2 problem. All right. So we have impending motion at some points at some surfaces. What surfaces are those? Where do we expect impending motion? Between A and B. Between A and B. Where else? And between B and C. B and C. Okay. Of course, we expect some motion here, all right? Some impending motion there and there. And between C and D, no impending motion. So here we'll be required to check for slip after we calculate everything. Okay. So let's draw this. We need to draw this separately since we have a lot of blocks. Let me say, okay, like so. Okay, okay, I just make them short, a little bit short. That one, like so. All right, I think this is enough. We just make them. So we have this one. Sorry. So 1, 2, 3. So 1, 2, 3. Great. All right, I think this is fine. I'll delete the spaces in between. So we have 1, 2, like so. Okay. So there we go. This is good enough, right? So we have the three blocks. Okay. So let's draw now. So here we expect some W. We expect some W1. We'll call it WA. This is block A. And then here we'll have some W2. I mean WB. And here we'll have some WC. All right, so here we are going to have some tension force there like so. All right, and then here we have the P. And then let's now the friction. So this first block, due to this tension force there, we expect the friction force to be in this direction like so. Let me use, I think, red. So we are going to have the friction force in that direction, and let's say we have the normal force here like so. All right, and then here we are going to have the same reactions. Here we'll have the same reactions like so, and then we'll have the same reactions like so. Okay, right? And then here we are going to have the friction. We are going to have the friction in this direction like so to oppose this motion, and then we'll have the normal force, let's say somewhere there. We'll have the normal force. Sorry, I'm just trying to have some space. And then we'll have the reaction like so. And then in that manner like so. And then here, let's say we have the normal force here. Of course, this block will also experience some kind of friction in this direction, okay, to oppose that motion, and we'll have some normal force like so. Right, so let's label this. So we are going to call this one WA. This is block A. This is block A. This is block B, and this is block C. So WA, let's call this one just T. This one is P. Okay, this is WB, and this one is WC. Okay. Yes. This one is, let me write this inside the block so that we have a little bit of space. So let's call this one as WB, then this one as WC. Okay. Let's label this. Let's call this as our FA, then this one as our NA, and then this one here is FA, of course, the one equilibrating. Let's call this one here is FB. Of course, these ones here as NB. This one here is FB. Then let's call this one as FC, and then this one as our NC. Okay, are we done? We are not. We just draw the last one. So we are going to have, of course, we don't expect to calculate these ones. We are going to have this value here, value of x, this one there, this one there, this one like so, and also this one here. Okay, we're going to have these values. So these values, let's label them. Of course, this is, we're going to call this as XA. So this one is XA. We call this XA. This is XB. Going to call this as XB. And this one as XC. Okay. So how many unknowns do we have? We have number of unknowns. We have, which is equal to, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let me count again. 1, 2, 3. XB. Okay. So we have XA, we have XB, we have XC, we have FA, we have FB, we have FC, we have NA, we have NB, we have NC, and then we have T, and then we have P. Right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have 11. All right. Then for each one of these, the number of equations for each separate body, there are 3. So 3 by 3. Number of equations of equilibrium, we have 9. Okay. So how many less? for us to have the same number of unknowns to be equal to the number of equations of equilibrium, they are supposed to be how many? They are supposed to be 11. So we need to invoke two more equations. So we'll say since motion is between A and B and C, so we expect FA, we expect some impending motion there. So this is going to be equal to mu S N A, and then we'll have also FB, which is equal to mu S prime NB. So this is equal to, what is mu S? Between A and B is 0.3, so this is 0.3 NA, and then mu prime between B and C, it is 0.4, so this is 0.4 NB. Great. Right, so let me just create a boundary here. I create a boundary like so. Okay, this is good enough. So then let's calculate. Let's find values of FA and A and so on. Okay, so we are on block A. We are on block A. So on this particular block, what do we have? So say summation of forces in the Y equal to 0 going up in our reference. Alright, so we have minus WA plus NA equal to 0. Okay, sorry. Okay, therefore our NA is going to be equal to, let me make mention of what WA is. WA is equal to 50 newtons. Therefore, our NA is equal to 50 newtons. Okay. Then we have summation of forces in the x direction equal to 0, going this direction being our reference. So we have minus T plus FA equal to 0. We know that FA is equal to 0.3 by NA, and we already know what NA is. Therefore our T is just going to be equal to 0.3 by 15. So this we get 15 newtons. Alright, so we are done with block A. Let's go to block B. We go to block B. Okay, block B. So we have summation of forces in the Y equal to 0, going up being our reference. What do we have? We have minus NA minus WB and plus NB equal to 0. We know that WB is just going to be equal to 25 newtons. Therefore, NB is equal to NA plus WB. Okay, we know what NA is. NA is equal to 50 newtons, right? Let me just move this a little bit in front like so, just a bit like so. Right, therefore NB is just going to be equal to NB is equal to NA, which is a 15 plus WB, which is a 25. So this gives us a 75 newtons, right? Great. So the Y we have WB, NA, and then NB. Great. So let's go to summation of forces in the X equal to 0, going in this direction being our positive. We have minus FA minus FB plus P equal to 0. And then we know that our FA is equal to 0.3 NA and our FB is equal to 0.4 NB. Therefore, our P is equal to FA plus FB. Therefore, P is equal to, so we know that NA, we know what NA is and NB. So it's just 0.3 times NA. What is NA? It is 15 plus 0.4 by NB. NB is 75. So this gives us a 45 newtons. So let's go down. Of course, we don't expect here between C and D, we don't expect any slip, but we need to check. We cannot be sure. So block C, let's do so. Block C, let's do the calculations. So say summation of forces in the Y equal to 0, going up in our reference. What do we have? We have minus WC minus NB plus NC equal to 0. WC, you know what WC is? WC is equal to 15 newtons. NB is equal to 75 newtons. Okay, and therefore our NC is just going to be equal to WC plus NB. Therefore, NC is just going to be equal to, that's a 15 plus 75. This gives us a 90 newtons. Right, and then summation of forces in the X direction equal to 0. Going this direction being our reference. So we have FB minus FC equal to 0. We know what FB is. FB is equal to 0.4 NB. Therefore, FC is going to be equal to 0.4 by NB, and then B is 75. So this gives us a 30 newtons. So let's check for slip. Check for slip between C and D. So let's find the maximum friction force between the boundary. So F maximum is equal to mu double prime S times NC, and we know that NC is equal to 90 newtons. Therefore, F max is just going to be equal to 90, and then mu double, let me write down this, mu S double prime is equal to 0.35. Therefore, F max is going to be equal to 0.35 by 90. This gives us a 31.5 newtons. Alright, so we have Fc, which is equal to 30 newtons. Is equal to 30 newtons. And this is less than F max, which is equal to 31.5 newtons. Therefore, no slip between C and D. Alright, so I guess we are done. We found the value of the value of P. We found the value of P, which is the minimum force. So this is the smallest force. This is P minimum. This is the smallest force that is required to cause impending motion. And the main impending motion will be caused between boundary A and B and between boundary B and C. Okay, you expect that to happen, right? Of course, when this particular block B experiences impending motion, it will happen between A and B and between B and C. Alright, I think this is about it. And I hope the video was helpful, and if it was, give me a thumbs up. I like my video, continue subscribing and liking my channel. Bye bye, and see you in my next screencast.